Hey, in this lecture I want to introduce the weak pointer, which is used in conjunction with the shared pointer. A shared pointer can be assigned to or used for the initialization of a weak pointer. Now, where is this weak pointer used? Well, it's basically used to provide access to the heap object that one or more shared pointer instances owns, but does not own the resource itself, and so it does not participate in reference counting. Okay, if you assign a shared pointer to a weak pointer, or you construct a weak pointer from a shared pointer, then we will not increment the reference count. With the shared pointer, there is a control block that keeps track of how many weak pointers that reference the heap object. But again, the weak pointer doesn't really affect the reference count, and I'll talk about the control block in a bit more detail later. I have an example of a declaration and initialization of a weak pointer. So I do weak underscore PTR, we pass in the type T, that can be a fundamental type or user-defined type. We give it a name such as WPTR for weak pointer or WP underscore, and so on. And then we pass in some shared pointer. The weak pointer does not have to be initialized to a shared pointer. You can assign a shared pointer to the weak pointer later on. And of course, as with the other smart pointers, we want to include the memory file for the weak pointer. Alright, so the weak pointer is a weak or non-owning reference to a heap object that is owned by one or more shared pointer instances. Okay, the weak pointer models a temporary or weak ownership. And with this, we can use the weak pointer to check whether the heap object is still alive or not. So it's kind of like a reference, but at the same time, it's not an alias for a shared pointer, because there are some operators that are not available for the weak pointer, such as the dereferencing operator and the arrow member access operator. Now, the weak pointer does not require the heap object to remain alive with an attempted allocation of the heap object. Again, remember that the weak pointer does not participate in reference counting. Now, why is this important? Well, it's important to prevent circular references between shared pointer instances, and we'll discuss this later on in the lecture. A couple of illustrations for you. Let's say we have a shared pointer and a weak pointer on the stack. We can either assign the shared pointer to the weak pointer, or we can construct a weak pointer by passing in the shared pointer for the constructor. As we can see from the illustration, the use count is going to remain 1, even though both of those basically point to the same heap object. And that's because the weak pointer is a weak reference to that heap object. The weak pointer again does not participate in reference counting. If the weak pointer was some other shared pointer, then of course the use count or reference count will be 2 instead of 1 here. But again, because it's a weak pointer, the use count will be 1. Now, if the shared pointer should go out of scope, then we decrement the use count. So the use count will go down from 1 to 0, and because of that, we deallocate the heap object. As we can see here, and the use count for the weak pointer is going to be 0 now, and we can actually check that using a use count function on the weak pointer as well. For another example, let's go back, and what we'll do now is, let's say the weak pointer goes out of scope, then the heap object is going to remain allocated, of course. Currently we have the use count at 1, so let's say weak pointer goes out of scope. Okay, as we can see, the use count is going to remain 1, the weak pointer does not affect the reference counting, and because it does not participate in reference counting, the heap object is going to remain allocated. This was a basic illustration. Let's go and look at a few examples in Visual Studio. Let's look at a few examples in Visual Studio. I include this memory file again for the smart pointers, and I have this entity class with the destructor and the toString and the setMember functions, again so that we can get an appropriate message printed out when we destroy or deallocate an entity heap object. Back in the main function, I'll go and create some nested compound statements. And I'll start off with a shared pointer. For this example, I'll call this shared pointer smart pointer because I'm actually going to change this later on to a weak pointer. But to get started here, I have a shared pointer, and within the inner code block or compound statement, I'll create another one here. Okay, I'll do something like this. In this statement, I'll assign the shared pointer, the inner shared pointer entity, to that smart pointer, and then I'm going to print this out in a use count. And I'll copy that, and I'll paste it down here in this outer compound statement. Now, of course, you can do toString and setMember if you want, but for this, I'm just going to keep it concise. Build around that. The build is successful, and of course within the inner compound statement we will get the inner use count is 2, and within the outer compound statement we will get outer use count is 1. Following that, the outer compound statement is going to go out of scope. The smart pointer here, the smart pointer object is going to get allocated down here when we reach the outer closing brace of this compound statement, and because of that we get entity destructor invoked. Because the use count is going to go down to 0, then we get the end of the program printout. As we've seen with the shared pointer, the heap object is going to get allocated when the reference count reaches 0. We've also seen that the reference count or use count will get incremented when we assign a shared pointer to another one or construct a shared pointer from another one. And both of those now own the same heap object. The weak smart pointer is a bit different, so let me go and change this here to a weak pointer. Now notice with this statement we are using the weak pointer here. The smart pointer is now a weak pointer, and that also has a useCount member function, which is going to return the number of shared pointer instances that share ownership of the heap object. Okay, so it's not actually to do with the smart pointer itself. It has to do with how many shared pointer instances actually manage the heap object. Let's build around this to see what we get. This will build around fine, and we can see that within the inner compound statement, inner useCount is 1. We get entity destruct invoked, member was 0. Then we get the outer useCount is 0. So what is going on here? Well, we get the printout right here, the inner useCount, okay, that is going to print out 1. Then we reach the closing brace of this inner compound statement. Then of course, the shared pointer entity goes out of scope. Now what we can see from this is even though we do this assignment, where we assign the shared pointer entity to that smart pointer, which in this case is a weak pointer, when program execution exits this inner compound statement, the shared pointer is going to go out of scope again, and it's actually going to deallocate the heap object, as we can see here. Okay, so we get that printout, inner useCount is 1, then we get the deallocation of that heap object. Then from the weak pointer we get this printout, outer useCount is 0. Okay, so the weak pointer useCount here, if we do .useCount on a weak pointer, then we will get again the number of shared pointer instances that own the heap object, or 0 if the managed object has already been deallocated. Okay, so it's going to be 0 here because no shared pointer is pointing to that heap object anymore. We have deallocated that, so the useCount for the weak pointer will be 0. Then we get end of program. Takeaway with this is that the shared pointer participates in ownership or reference counting, whereas the weak pointer does not. Another important thing to remember with the weak pointer is that it does not overload the referencing or the arrow member selection operator. For example, in this case we have an entity on the heap. Let's say we wanted to do something like this. We want to do smart pointer to string. We cannot do that if I try and build around that. Control B to build actually will get an error here. Get this error here does not have an overloaded member operator, the member selection arrow operator. Similarly, if I change this to an integer here just for a second, can I try and use the dereference operator as we can with the other smart pointers? We will also get an error. Control B to try and build that. We will get an error with this, and that is because no operator matches those operands. Okay, so the weak pointer does not have an overloaded dereferencing operator. Now to some extent this may make the weak pointer seem a bit useless, but what we can actually do is we can use the lock member function to return a shared pointer that now also owns that heap object. For example, okay, we use the lock member function of the weak pointer, and that is going to return a shared pointer, right? So from that, what can we do? Well, I can do something silly like this. I can return a temporary shared pointer. I can use the dereference operator on that. Build around that, we should get 55 here. And that is what we get 55 printed out. I'll undo this. We have a weak pointer passing entity for that, and a shared pointer with an entity as well. And I'll use make shared and I'll pass an entity for that. And then what we can do is, okay, this is going to return a temporary shared pointer which is going to own that heap object. The heap object that the smart pointer is basically pointing at, and then we can do toString on that. Build around that and we get 55 as we would expect. And of course, if you really want to, you can assign whatever this returns to a shared pointer. Now this inner useCount in this statement here, this inner useCount should be 2. Build around that. And you can see inner useCount is 2, entity destruct invoke member was 55. And then in the outer compound statement, the outer useCount is going to be 0 again because both of those smart pointers, both of those shared pointers go out of scope. So as you can see, the weak pointer is not entirely useless. We can use it. We just have to lock it basically. So we do the lock member function on that. And then we can either assign it to a shared pointer, or we can use the dereferencing or the member access operator on whatever that returns, which will be a temporary shared pointer object. Okay, a few more examples on the weak pointer. The weak pointer also has the reset member function, but it's important to note the difference between the reset member function of the weak pointer, the shared pointer, and the unique pointer. With the weak pointer, it is going to release the reference, but it's not going to deallocate the heap object. Let's just look at that. Okay, I'll do smart pointer.reset, so that is the reset member function of the weak pointer, and then in this statement right here, the use count should be 1, because in this statement, that smart pointer, in other words the weak pointer, no longer manages a heap object. So because of that, this here, the shared pointer to entity 2 is not going to manage the same heap object that this smart pointer entity is going to manage. And because of that, again, this shared pointer entity use count is going to give us 1. Let's just build around that so we can see what we get. We get inner use count is 1 instead of 2 as we had it before. Again, if I comment that reset statement out and I build and run, we should get 2. As you can see, we get inner use count is 2 now. Again, there's a bit of a difference between the reset member function of the weak pointer and the reset member function of the shared and the unique pointers. Another interesting member function of the weak pointer is this expired member function that we have right here. And so I'll just do bool alpha here, and then I'll do this statement here, weak pointer expired, and then I'll do smart pointer dot expired. And this expired member function is going to return true basically when the smart pointer use count is 0, so when it does not reference a heap object. Again, this expired returns true if the reference heap object has basically been deallocated unless the weak pointer never referenced the heap object to begin with, and false otherwise. So in other words, it's going to return false if the weak pointer does reference a heap object. Pull around that. And that should give us true now. You can see that gives us true. Whereas if I move these lines within this inner code block, it should give us false. Okay, so I'll just pull around again. And you can see we get weak pointer expired, that is false. Then we get entity destruct invoked, and of course that is because when program execution reaches the statement, the shared pointer still exists, it hasn't gone out of scope yet. And because of that, the heap object still exists, so the weak pointer still references that. Okay, so that was a quick look at the expired member function and the reset member function as well. A couple more things before I wrap up this example. So we have the weak pointer in the outer scope and the shared pointer in the inner scope. So I'll switch those around. And I'll go ahead and remove some of these statements. Okay, what I want to demonstrate with this example is, again, we have the weak pointer within this inner scope now, and when the weak pointer smart pointer goes out of scope, you will notice that it does not have an effect on the use count. Okay, so the use count within the inner scope is going to be 1, and when the weak pointer goes out of scope because we reach this closing brace, then the use count within this outer compound statement is going to be 1 as well. So let me build around that. Okay, as we can see, the use count within the inner compound statement is going to be 1, and the use count within the outer compound statement is going to be 1 as well. And then when program execution goes out of the outer compound statement, then the entity destruct is invoked, we get end of program. That is down here, of course. So again, all I want to demonstrate here is that the weak pointer does not affect the reference count. Okay, we assign a shared pointer to the weak pointer in this statement, but that does not increment the reference count. We only get 1 in this statement. When the weak pointer goes out of scope following this inner compound statement, it also does not decrement the use count, so we get 1 again in this output. And then one final thing, we have the get member function with the shared and with the unique pointer, but not with the weak pointer. So what do I mean by that? Okay, the weak pointer does not have a get member function. If I Ctrl B to build, we'll get an error. So I'll comment that line out and we'll move on to the next example, which will focus on circular references. In this section, I want to introduce circular references. Sometimes where we have a strong ownership, in other words, where we use shared pointers, we can leak memory, again in the case where we have a circular reference. To avoid that, to solve that problem, we can use weak pointers instead of shared pointers. Now to get started, we have this class entity here, and we have a shared pointer to an entity, and I'll just call that shared pointer member. Now of course we can have a shared pointer, let's say in the main function, that owns an entity on the heap, and that entity has a shared pointer as a member that also owns some entity, right? And this can create a circular reference. So let's go and look at a few illustrations on that. In this example, let's say we have two shared pointers, shared pointer entity 1 and shared pointer entity 2, and those both manage entities on the heap. So entity instances, as we had it in the previous example, those entity instances has as members shared pointers themselves, which can also manage entities on the heap. Now the strong ownership with the shared pointer is going to prevent the allocation, and that will lead to a memory leak, as we'll see later on in the example. Let's take a closer look at those entity heap objects. The use count for those will be 2 because we have a shared pointer on the stack that owns each one of those entities. So shared pointer entity 1 owns the top heap object, but you will also notice that the bottom entity on the heap, that instance as part of it, remember, has a shared pointer that also owns the top heap entity now. And the same thing with the shared pointer entity 2 on the stack that owns the bottom heap object, but that bottom heap entity is also owned by the top heap entity. Okay, remember that class has a shared pointer and that is currently pointing to the bottom heap entity. So that is why the reference count for both of those heap entities is now 2. Okay, let's say at some point during program execution the shared pointer entity 1 goes out of scope. Then of course the use count for that entity on the heap is going to get decremented. So the use count for that top entity on the heap now, or the reference count for that, is 1. Later on in the program, the shared pointer entity 2 may go out of scope. Let's say we exit some function scope or something like that. So shared pointer entity goes out of scope, it gets destroyed. The reference count for the object that it managed is going to get decremented. So the use count or reference count for the bottom entity on the heap is now going to be 1. And as we can see, we have a memory leak. Those two heap entities keep each other alive. The top entity on the heap has a shared pointer, which owns the entity on the bottom of the heap, and the entity on the bottom of the heap has a shared pointer, which owns the entity that is on the top of the heap. And because of that, the reference count for each one of those entities is going to remain 1, and they will not get deallocated. And again, this causes a memory leak. We can fix the memory leak by having a weak pointer for the entity class instead of a shared pointer, because with that weak pointer we have a weak reference which is going to allow for heap deallocation. As we can see in this example, on the stack we have the shared pointer entity 1 now. Maybe in the main function we have a shared pointer which owns an entity, and the same with shared pointer 2 entity 2 that also owns an entity at the bottom of the heap. You can see that. So again, on the stack we have shared pointers that manage entity heap objects, and you can see those entity heap objects now have weak pointers, and because of that the use count for those entity heap objects is going to be 1. They are owned only by the shared pointers that are on the stack. So let's say shared pointer entity 1 goes out of scope again. That will decrement the use count for that top entity heap object, and because of that, that entity heap object will get allocated properly. And the same thing for the shared pointer entity 2 on the stack. Let's say that goes out of scope. Then we decrement the reference count for that bottom heap object, and because of that the bottom heap entity will get allocated successfully. And as we can see, we no longer have that memory leak problem. Here's another example where strong ownership prevents the allocation with different classes. We have entity A and entity B. Those are basically different classes, and so we have different instances of different classes on the heap in this example. And as you can see in this example, on the heap, entity A is going to keep entity B alive, and similarly entity B is going to keep entity A alive. How do we fix this issue so that we do not have a memory leak? Well, we can use weak pointers instead. Okay, a non-owning or weak reference allows for the allocation, and we can do that using the weak pointer. And with this we have to decide who owns who. So in this example, entity A owns entity B, and because of that we want the class entity B to have a weak pointer instead of a shared pointer. Again, in this example these are different classes, so the class entity A has a shared pointer and the class entity B has a weak pointer. So when we instantiate these on the heap, the entity A is going to own entity B. In other words, the use count for entity B is going to be 1, but the use count for entity A is going to be 0 because entity B has a weak pointer, not a shared pointer. This is how you solve that circular reference problem. Also, it's important to note that a circular list can be longer than 2 objects, also referred to as nodes. And to break the cycle, the last node should hold a weak pointer instead of a shared pointer. As we can see here, the shared pointer of entity A owns entity B, and the shared pointer of entity B owns entity C. But entity C has a weak pointer to entity A, and that is going to break that circular reference problem. Let's look at an example of this. So I have the entity class again, but in this example, I have a constructor which is going to do cout entity construct invoked. And as before, the destructor is going to do entity destruct invoked. In this example, the member has changed as well, so the member is now a shared pointer, so I do sp_member, and that is of type shared pointer entity, alright. And the shared member function has also changed, so I do void shared member. The formal parameter is a shared pointer entity in this case, so that is sp_entity p for shared pointer entity parameter. And in the body of that, I'm going to assign shared pointer entity parameter to the shared pointer member, alright. In the main function now, I have these two shared pointers, entity A and entity B, both of this type shared pointer entity, and use make shared and I pass an entity for that. I'll actually just rename this here, just to make it clear that these are shared pointers. And if we build a run now, we get entity construct invoked twice. And of course, once our shared pointers go out of scope, we will get entity destruct invoked twice. So both of those entity heap objects will get allocated successfully. But let's say we go and use that setMember function now. Actually, the setMember function in the entity I'm going to change to a reference. I'll just make that a reference to a shared pointer entity constant. And then here we do shared pointer entity A, setMember, and we pass in shared pointer entity B. So remember, shared pointer entity A manages a heap object, and we call the setMember function on that heap object. The member of that heap entity is a shared pointer as well, which is going to basically manage or point to whatever the shared pointer B now points to. And the same thing for this here, and actually this should be shared pointer entity B right here. So we do a shared pointer entity B, setMember, we invoke setMember on the heap entity that the shared pointer B owns, and we pass in shared pointer entity A for that. And again, because we are working with shared pointers, that is going to create a strong relationship. So if I build around this now, we get entity construct invoked twice, but we do not get any of the destructors invoked. And as we've seen, the solution is to make this a weak pointer instead. And of course, as we've seen in previous examples, it is fine for us to assign a shared pointer to a weak pointer. So I'll actually change this here to WP for weak pointer member, and I'll build and run again. Now we get entity construct invoked twice, and then we get entity destruct invoked twice as well. So we know that those two heap objects are deallocated properly. A similar thing is going to happen if we have different classes, of course. So currently we only have this one entity class, and I'll duplicate this, but before I do, I'll change this back to a shared pointer, and then I'll go and copy this class. I'll rename those classes to entity A and entity B, but of course you can use something like class A, class B if you want. Also, you can use the find and replace functionality if you want to use that, but I find the copy and paste is quick enough for this example. So what we want to do is we want this class entity A to actually have a setMember function with a different parameter. So we want to use entity B for the parameter, and the same thing for the member to make sure we have the correct type. Then for this class B, we want to make the formal parameter a reference to a shared pointer, and I pass in entity A for that, and the same for the member. And of course, if you want, you can change the name again. Okay, so SP for shared pointer. Now in the class entity A, we are using the entity B right here for the type of the pointer that the shared pointer manages. So to make sure that we don't get any problems with that, because if we go and comment these lines out here, and we try and build, we'll get an error. In this line, for example, where we have the shared member, we do entity B, and we will get an undeclared identifier. So pause the video for a second and think about how we can fix this. Alright, of course, we're going to use a forward declaration for this. Control B to build, and that should build fine. Okay, I'll go back to the main function now, and let's see what we have. I will change the shared pointers in the main function, so we pass in the types of entity A and entity B for those shared pointers now, and the same for the make shared functions. The setMember function statements will remain the same. Now if I build around this, we should not get the destructors invoked. And as you can see, we get the constructors but not the destructors. So what we have to do with this is we need to make sure we understand the relationship. So in other words, which one of those classes is going to have the strong relationship. One way of doing this is to think in terms of entity modeling. So let's say class entity A is class business instead, and then class entity B is class employee instead. Then of course you can think in terms of a business has so many employees, so that has a relationship or a strong relationship, and because of that the business can have a shared pointer, and you pass in the employee for that, whereas the weak pointer is going to be in the employee. Okay, I'll do a quick example on that shortly, but let's go with the entity B here. We'll set that to a weak pointer, and that should break the circular reference problem, and we should get the destructors invoked now. So let's build around that. And we should get the constructors invoked, and we get the destructors invoked as well for both of those heap entities now. Okay, for a final quick example, again, we can think in terms of has a relationship. So the business has employees. So that is a strong relationship. All right, just a silly example. And then the employee has a weak pointer to the business. I'll change the name of the member to weak pointer member. And in the main function, I'll update those shared pointers. So I'll pass in business and employee for what the shared pointer manages and also for what we have constructed on the heap. And the set member functions I'll leave as is. And if I build one now, we will get business constructor invoked and employee constructor invoked. And then also business destructor invoked and employee destructor invoked. Whereas again, if this changes here to a shared pointer, and we try and build that, then of course those destructors will not get invoked again. Right? And I'll just undo that. Okay, I know this can be a bit confusing. That is why I did so many illustrations, but hopefully the section makes sense and illustrates why it is important for us to have the weak pointer. A summary on the weak pointer member functions that I discussed in this lecture. The lock member function is going to return a shared pointer that owns the heap object referenced by the weak pointer, and if the weak pointer does not reference an object, then the returned shared pointer does not own a heap object. Okay, so that shared pointer is not going to manage an object because the weak pointer is basically null, and so that shared pointer will also be null, also referred to as empty, so the weak pointer or the shared pointer is empty. Okay, and then we have the useCount member function, which is going to return the number of shared pointer instances that own the heap object. This will be 0 if the heap object is empty, so in other words, if it does not reference a heap object. Then the reset member function is going to release the reference, but it's not going to deallocate the heap object as it would with a unique pointer or a shared pointer. Finally, the expired member function is going to check if the useCount is 0 basically. It will return true if the weak pointer does not reference a heap object, otherwise it's going to return false. I also mentioned that we do not have the get member function available with the weak pointer. Alright, that is going to wrap up this lecture. I'll see you next time.